So let us start with general MPNNs, okay? In this specific part, we look at undirected, unlabeled featured graph, okay? So you have a set of nodes, V, a set E of edges, and the embeddings, okay? Mapping every node to a vector of dimension D, and we denote it by small x of V, okay? The embedding of V. Okay, and again, we'll generalize to heterograph in the next part. Okay, now, as usual, we'll look at X as a matrix in RV times D. Okay, essentially choosing basically a row number for every vertex, and this is going to correspond basically to the adjacency matrix A, okay, which is a symmetric, just symmetric with matrix with entries in 0, 1. Okay, and again, for both the adjacency matrix on X, we assume that there is some ordering V1 to Vn of V. Okay, now we look at the graph architecture, graph model basically with parameters as a function fd theta, okay, that takes as input a graph, featured graph, okay, and the assignment to its sequence of parameters, and it produces the result. The result is basically a representation or a vector of length k for every node in V. Okay, and this means that we basically look at tasks of multivariate node regression, okay, where we map every node to a vector. And you can look at other tasks. We will mention these actually, the graph level tasks, which are different, but we'll mainly focus on node level regression, multivariate regression tasks. Okay. Of course, with the case of a k equals 1 is where we have standard node regression. So this is an architecture, as usual. It has parameters. And when we learn these parameters, we set specific values to these parameters, what we get is a model, a graph model. Okay? And D of the node features, the input node features. Okay. So it is convenient, it will be convenient to look at some of these representations of MPNNs as not as operating on graphs, but rather on operating on the usual objects of machine learning, like matrices. Okay, so instead of looking at a function of G, we'll look at a function that gets the matrix A and the matrix X. Okay, and so we may write FAX with the parameters of theta. Okay, so what is the problem here? What is the issue of coming up with a graph model? So suppose that one says, something that is, well, not really well defined, but say, well, let it be an MLP receiving basically the rows of A, the vectors of A, and the feature vectors of the nodes, A1 to AN and X1 to XN, and the parameters, and that will be some MLP on top of this vector, basically concatenation of many vectors. Okay, now what are the problems with that? So one thing is that we would like to learn a function over one graph and apply it to another graph. which means that the number of inputs, the dimension of the MLP varies. This is something that is impossible. An MLP needs to know its dimensions when you learn it, when you generalize it to your future instances. Okay, so how do we generalize across graphs? And another thing, the MLP, basically, if you define it in this way, it is actually sensitive to the ordering of the nodes. It actually matters whether you call x1 and not x3. If you decide to label a node as the first node or the third node, that's going to change for the MLP because it doesn't know that it needs to, treat uh, isomorphic graphs really in the same way. Okay, so it is sensitive to the actual ordering of the node, which is bad. Okay, this is not something that we want. This is just an artifact of the representation of what we do. And in the end of the day, if you represent it in this way, how does the MLP take into account the graph structure? Where is the graph structure? Basically, in order to understand that node 1 and node 7 are neighbors, you need to look into what these vectors of A include, and from that infer the structure. That's a lot to ask for from an MLP. Okay, we are for sure going to miss this structure. So we need something that accounts um, directly, easily, gracefully to the structure of the graph. Let's talk about more about this idea of node reordering or node order, sensitivity to the order of the nodes. What exactly is it that we want? So to be more formal, we're talking about a permutation. Okay, we want the model to be non-sensitive to the permutation. So a permutation is just a, a bijection basically over the set of numbers 1 to n. Okay, and basically saying that we reorder v1 to vn to be v pi of 1 to v pi of n. That's a permutation. Now we associate a permutation with a matrix P, okay, that is defined by Pij equals 1 whenever pi of I equals j. Now, when we permute the nodes of a graph and we basically rename the vertices according to the permutation P, what we get is the matrix A pi, the permutation pi, sorry. Then we get the adjacency matrix A pi. And to obtain A pi, we simply, multiply it by P from the left and then by P transpose from the right. The left multiplication reorders the rows, and the right multiplication, P transform, reorders the columns. Okay, so we basically get the new representation. Okay. Also for the feature matrix, okay, we basically need to permute the rows to correspond to the new ordering, the new names of the or indexing of the vertices. So it becomes P times X instead of X. Okay, so X pi is P times X. Now, for a function, what is it that we want? How do we define, being indifferent to the node reordering? So we can think of F being permutation invariant, which would basically mean something like F applied to the permuted A, comma, the permuted X is equal to F before the permutation, right? That's what permutation invariance means. Now, if we're looking at graph level tasks, this is what we want. But for node level tasks, that doesn't make sense. It just means, if you're reordering the nodes, now, V1 becomes V7, you still want to have the same result in the first line and the seventh line. That doesn't make sense. What we actually want is the value to be reordered accordingly. So F on the permuted A and the permuted X is equal to P times the result of the original graph. Okay, this is what we want. So this is called permutation equivariance, not invariance, equivariance. And this is basically what we want. And we will discuss models that are all equivariant by definition. Okay, now sometimes it will be obvious, and in some cases we may need to think of it. They may require some more thinking, but most of the cases, you'll see that the way we define them, they are obviously equivariant. Okay, but this is an important property of GNNs. Okay, so again, some intuition on message passing GNNs, on MPNNs. Okay, so we compute a value, is representation HU for every node U. Okay, we start with HU being the original features, the input features, XU. Then basically we have rounds. U collects the values of HV from its neighbors V and updates HU by some function of these embeddings. Okay, so the value of U accounts for the values of its neighbors. And then we do it again. We again update the values of the value of U by updating the values of HV. And we do it for every node. Okay, so the values of the neighbors V are themselves updated in the first round. Okay, so basically what we do in the second round is that we account for information that is in the two-hop neighborhood, not just one hop. Okay, and we continue with that, applying basically L steps. Okay, and therefore the value of a node, the representation, the embedding, the vector of a node accounts for its L-hop neighborhood. Okay, now we need to make sure that the resulting function is equivariant. Okay, in particular, it's not sensitive to the ordering of the neighbors. So we're going to define it in a way that this updating function collects data from the neighbors in a way that is insensitive to the ordering of the neighbors.